Very much, Carsten. So I'd like to start by thanking the organizers for managing to localize basically everyone during this week in this really nice and exciting place. I know it has been very hard work, so well done to you guys. So first of all, my people who were involved with the work that I will describe, Jack Cohen and Mason, two my students, and Suropriya Saha, who is a student of Shriram Ramaswamy in Bangalore, and Yaha Ibrahim, who is a student of TANI Liverpool. And I'd like to also, part of the work I will describe is done joint with Rodrigo Soto from Chile, who was a sabbatical visitor with us this year, and the experimental team in Sheffield. So basically, this is the outline of my talk. I would like to see how we can take colloids that are dead and make them active, and then basically try and understand when they are active how they are different from equilibrium, sort of Brownian particles. And then there will be some details about exactly how they respond to external field and interact with potential external field, which could be used to study the interaction between these particles themselves, because when they are active, they create these fields that will affect other colloids and so on. And as you can see here, these are movies from the experiment in Sheffield. You can make these active colloids do things in a controlled way. So this one is spinning around, this one is tumbling around the circular trajectory, this one is going on a straight line. What I want to use as a basic mechanism is phoretic transport phenomena. These are non-equilibrium, but within linear response regime transport phenomena that are familiar from a long time ago. So earlier references you can see are from the 19th century. And the big advantage of these mechanisms is that they are force-free in the sense that they do not involve an external force that will sort of mechanically be applied to them to move them, so that we can, if we can get the mechanism which creates the gradient basically on board somehow by producing asymmetric sources and so on, then we can make something which will self-propel. In particular, I would focus on diffuse geophoresis and thermophoresis throughout the talk. As I said, these are interesting mechanisms. They are a little bit delicate, and I don't want to make this talk a talk about diffuse geophoresis. I want to see what we can do with it, but I just want to make it a point about basically how we should think about these. So it's very tempting to think of this problem, let's say, of a particle in a gradient of solid molecules in this picture, in which we basically use this concept of osmotic pressure, which we're familiar with from equilibrium, and basically use that to calculate some net force which is exerted on the colloid, and say that so far I have removed the fluid, and then introduce the fluid by just saying this. All it does, it will introduce a viscous drag using the Stokes equation, and then balance the two. If you do that, you actually get velocities that are really, really large, orders of magnitude larger than they should be. And what's also, what will also be seen is that the direction of motion of the solid molecules will be different to what will turn out to be in diffuse geophoresis. So diffuse geophoresis gives you a stationary profile of the colloid and the solute molecules that can move together in one direction with the same average flux, which means that if you go to the co-moving frame, you see a stationary profile. And that will not be the case if you use that kind of picture, simplistic picture. Okay, so let's do this self-diffuse geophoresis. All we need to do is get a colloid and cover it asymmetrically with a catalyst, let's say, and put it in a solution of a molecule that the catalyst would break down. When the catalyst does its job, it will break these molecules into, say, more molecules. So as you can see now, there's a gradient in the number of particles, and then each of these solute molecules will interact with the surface with its own interaction, and that will cause propulsion. And the direction of propulsion will be determined by whether the interaction between solid molecules and the surface is predominantly repulsive or interactive. And this is basically those force dipoles, whether they are like this or like that. And that will determine the direction of motion. And now, because we are at the Newton Institute, I'd like to add a remark by way of acknowledgement. Actually, we did this work with Tanya Liverpool in March 2004. Here at the Newton Institute, there was a workshop on biophysics, and we were sitting through these talks about molecular motors that were going above our heads, all these details and complications, which we didn't understand. And then at some point we said, look, let's back off and just, start from scratch, put in simple ingredients and see how you can make something which will do basically convert chemical energy into mechanical work at small scale, and try to study that. And at that time, we were not aware, as serendipity had it, that exactly at the same time, a brilliant synthetic chemist called Ayushman Sen was doing experiments with bimetallic catalytic rods in Penn State University, and he discovered that they self-propel. So all of a sudden, this was not just a theoretical exercise, but it was basically a very exciting possibility to look into the active motion of these things, because they could be made, and so on. As it turned out later, the exact details of these two mechanisms are different slightly, and I think we have a fair understanding of both of them. For example, this one moves towards the platinum cap, self-diffuse phoretic one. If you only have coated with the catalyst, and you have the same reaction, it moves away from the platinum cap, etc. And this is essentially, if you want to have a simple picture of this particular model, it's a short-circuited inverted battery. So you take a battery, it has electrolytes inside, it has two pieces of wire, you short-circuit it, and then you turn the electrolyte into the solution. What you do is you exchange ions and electrons in two different places at two different speeds or diffusivities and rates, and that gives you relative fluid motion. In fact, you can get a similar effect with an LED. If you find a small enough LED that can float in water and you shine light on it, it will swim as well with the same mechanism. Okay, well, depending on how small it is and so on, but yes. Measurable. There is a paper on this. So.
So one that's big enough to be seen by the naked eye will move at a speed that the naked eye
yes.
can be patient enough to watch.
Yes, it's not my work, it's somebody else. I don't have the reference now, but yes. Okay, so diffusive phoresis is difficult to understand perhaps, but it's very easy to analyze. You just take your Stokes flow outside of all this boundary layer, which is where everything is happening, and introduce the slip velocity as a boundary condition, which is basically set by the tangential gradient of the concentration. And here I'm just using one concentration, so in reality you have the reactants and the products, and each of them will set a different boundary condition for the slip velocity of the fluid. There is always this response parameter, which I call mobility, and I use the symbol mu for it, and this is essentially an off-diagonal Onsager coefficient within this linear response theory that I'm describing, and it can be both positive and negative, so velocity could be away or towards the concentration gradient of the solutes. And as you can see here, the mobility is controlled by kT over viscosity of water. There's this little length square that I would like to call Deryagin length, because Deryagin was the first person who described diffusive phoresis and made experiments on it in the late 50s and early 60s. And as you can see, this is basically the range of the interaction potential between these molecules and the surface of the colloid. Then you couple that to the reaction diffusion of the surfactants, the solute molecules in the bulk with the right boundary condition on the surface of the colloid. What you see here, this parameter alpha, is what I call the activity. So that's essentially the rate of introduction of excess solute molecules in the solution, or so if it is acting as a source, or removing molecules if it is acting as a sink. So alpha is basically what's driving the system away from equilibrium and could also be both positive and negative. If you do the maths, swimming velocity turns out to be proportional to alpha times mu divided by the diffusion coefficient of the solute molecule, the characteristic one that I'm using here. So essentially, I have this activity parameter times the off-diagonal Onsager coefficient divided by the corresponding diagonal Onsager coefficient, which is always positive. This can work for any phoretic mechanism. You just need to use the right transport coefficients here, and there you have your velocity straight away, apart from the prefactor, which depends on the geometry. Because it's so simple, you can ask all kinds of questions about the right type of symmetry breaking. Do you always have to have symmetry breaking in the activity, as I had in the earlier sketch, the catalyst, or is it okay to, is it sufficient to have symmetry breaking in the mobility? Can I couple this to shape? Is a rod a better self-diffuse geophoretic colloid than a sphere or a disk? And so on. You can ask all kinds of questions like that and play with the sign of these mobility and activity coefficients. And also, as I said, it could work for any phoretic mechanism, and in particular, I would like to talk later about self-thermophoresis. So that's motion of colloids under self-generated temperature gradient, which can be caused, say, by irradiation. Okay, so here I have a slide about experiments. We did a few experiments on these to try and understand them and see if they work. And basically, I really would like to understand how this whole mechanism depends on, say, the size and the type of chemical reaction that you use, fuel concentration, and so on. And as you can see already, there are some complications. For example, you could get a size dependence if the size is larger than a certain threshold. You could get Michaelis-Menten type behavior, so initial linear growth or dependence of the velocity on the fuel concentration, and then eventual saturation, which adds a nonlinearity to the problem, and so on. You can have different types of behaviors. And for people who are interested in records and so on, because I know there are some groups who basically go to the Guinness Foundation and basically report what they achieved. Actually, these self-diffuse phoretic colloids are not that slow. I mean, you can get them to move as fast as, well, this point is 37 micrometers per second for a diameter which is 500 nanometers, 0.5 microns. And in fact, this is, we have an ongoing collaboration with TANI Liverpool to try and understand how we can basically read the catalytic chemistry of what's happening on the surface of these colloids by just doing video microscopy. So you just do particle tracking, you do it for different parameters, you do mean squared displacement, extract these parameters like velocity and so on, and then you tell, aha, this is the right, say, kinetic pathway, a multi-step with this property, and that one is wrong because I can extract that from my particle tracks. And this is, I think, a very interesting prospect, because alternative way of determining theoretically without without assuming anything is to do quantum chemistry, which at finite temperature is very difficult, and so on.
What's the mechanism of rotational diffusion?
So mechanism for rotational diffusion is, actually this slide is on rotational diffusion, is thermal fluctuation. So you have a colloid with large enough surface, it gets kicks from the thermal bath. These will basically move it around, but also will generate rotational orientational fluctuations, which will have, there's a formula for the rotational diffusion coefficient, which is basic KBT over same combination viscosity of the solvent and cubic power of the size. In fact, they always pick the longest length scale in the system. So, okay. They don't always go on a straight line, of course, in reality, so we need to look at their stochastic dynamics and extract the type of behavior they can have. And as it turns out, there are typically three time scales in the stochastic dynamics of an active colloid that is made like that. The longest one is the rotational diffusion time that John talked about. So that's basically the time the colloid can keep its orientational memory, which means that when it has this self-propulsion thing going on, it can move on a straight line for that time scale. And then after that, it gets a kick and forgets the previous orientation. There is this time scale tau d, which is basically the characteristic time scale for relaxation of, say, a concentration profile around the colloid. So let's say our colloid is moving in this direction because the cloud is already built up with the right shape. If the colloid itself turns for whatever reason, the catalytic patch which is on it and the cloud around it will equilibrate to the new orientation after this time, which goes like r squared divided by the diffusion coefficient of the solute molecules. And then there's the vorticity diffusion time, which is the characteristic crossover time between inertial and viscous behavior in the fluid dynamics itself. And as it turns out, if you just put in numbers, I think in most imaginable cases, there's a very good separation of time scale, which means we can have all the 4 different regimes experimentally accessible in principle. And as you can see, we can get interesting types of stochastic dynamics. And in particular, there is this type of dynamics which is possible for a fully coated catalytic sphere. So just take a sphere and fully coat it with the catalyst. It undergoes anomalous fluctuations, which is basically like t to the 3/2. Because it's not quite, so it's not propulsive because there is no symmetry breaking for the orientation, but the cloud of solute around it is basically fluctuating all the time, and it's polarized all the time, which means it generates these large kicks that are over, so basically stronger than normal diffusion. Okay, so now, as it turns out, and was mentioned by Anna yesterday, this meeting has developed this unusual theme of probing into the private lives of weird creatures. And because it's Friday afternoon, maybe it's time to ask questions about the relationship habits of these active colloids. And as it turns out, it's complicated. So you'll see what I mean by that. Basically, if you go back to this picture, and this was mentioned by John Brady already, the concentration profile, which is generated by a colloid with activity alpha, decays like 1 over r. This is basically similar to Coulomb or Newtonian gravitational potential. But this is the field that's created. The other particle will have to decide what to do with it and how to respond to it. And it turns out that the relevant charge for that other particle is controlled by another parameter, by the mobility, which is mu. And that means that different particles can have different tendencies towards each other. So basically, this one can be attracted to this one, but this one can be repelled by that one. And this is recipe for some really interesting activity, dynamical behavior, which we study. So in specific terms, basically, the velocity of the first one is proportional to activity of the second one times the mobility of its own, and vice versa is correct for the second colloid, which means they don't have basically action and reaction are not the same. Okay, so what we do here is just a simple Brownian dynamic simulation for a number of these colloids. We assume that they are uniformly coated, so we don't, at this point, we don't include self-propulsion and orientational coupling and so on, which are complicated. Basically, if you non-dimensionalize these Langevin equations and extract the velocity, effectively you have 2 types of charges. We have these alpha tilde for each particle and the mu tilde, which are basically numbers of order unity of either sign, and we can decide what they should be. And we add the normal thermal noise. We also add exclude volume effect when they get close to each other so that we can see formation of basically self-assembled structures. But we keep the form of the interaction to the far field approximation, which is what I have here. So this is not exact all the way to particles getting close to one another. And also we ignore hydrodynamic interaction at this point. So what we see is there will be dynamic self-assembly. Things form, you can call them molecules, and they will have different types of activity depending on the symmetry of what is formed. And basically you could get all kinds of possibilities. So here let's say we only focus on these 2 particles. So you need to keep this in mind. Particle A has positive activity and positive mobility, and particle B has negative activity and negative mobility, but the values are different. So we'd like to play with this. Yes?
mobility come from? You need to put a force on it and it moves in the opposite direction?
So negative mobility means if there is a gradient, it doesn't go away from it, it goes towards it.
Gradient concentration.
Yes.
Oh, okay.
So this particle generates, creates a concentration gradient, the other one senses it and moves towards it. Okay. So this is one particular example. We chose B to be at relatively, so moderately, let's say, active and attracted to A. And we chose A to be positively active and indifferent to B. Right? You can make your own decisions about the social implications of what you're about to see. And we start in the dilute regime and we run the simulations. I'll let you watch it once and then I'll talk. So A is the yellow one or the orange one and B is the blue one. You can call them Alice and Bob if you want.
Not a ménage à trois.
Okay, so initially, basically, they are in the dilute form and they don't see each other, and then AB molecules form fairly quickly and they are active, but as it turns out, in this particular temperature, they are not stable. So in this temperature is down here, and on this temperature, the stable molecule happens to be AB2, which is, by the way, not neutral. And I'll talk about neutrality later, because we're generalizing these concepts from electrostatics. As you can see, there are scatterings, so you know, ABs could come and find a lone B and form an AB2 and move off. They could form AB4 instantaneously, but that may not survive for a while, and so on. But you can look at the statistics of these molecules and see what kind of, so I don't know if you just saw, there was a scattering event in which a B was recruited.
Are these all in the same plane?
They're all on 2D. We use the three-dimensional potential, 1 over R, but choose a two-dimensional just because the phenomenology is more familiar here, and we don't have the Kostelis-Towers transition and so on. Okay, so neutrality in a given molecule, if basically alpha is the rate of creation of the same solute molecule and B is the rate of its removal, then neutrality basically will tie these two values together. And here you can see that you don't completely, if you want, you don't fully satisfy the valence of this structure. We can go ahead with this and with this game and tabulate the molecules that we find. So I should remind you, actually, these lines that you see here, or different plots that collapse on top of each other, they are different concentrations, all within the dilute range. So they are, let's say, 10 to the minus 4, 10 to the minus 3 range, but they are different. And we start them from different conditions. We vary the temperature, which is this parameter d tilde here. That's the effective dimensionless diffusion coefficient of individual colloids. As you can see, at low temperatures, in this case, AB2 is the most stable molecule which forms, and then at some point it gives way to AB, which happens to be dynamically more favorable in that situation. Both of which are active. Yes.
Do you always start with more blue than yellow?
So with the number of, that's a good question. I should have put that. The number of blues and yellows are basically decided by the overall neutrality of the system, because all the A's are generating the solute and all the B's are removing them, and I want the system overall to be in stationary state. So the total number of A's times alpha should be equal to the total number of B's times alpha B, so that I have overall. So if I choose the number for one of them, the other one is determined automatically. Okay, so we can tabulate these, and these structures that you can see here are examples of stable molecules that we find. So these are not random snapshots of loosely sort of fluctuating clusters that we find. These are stable molecules that will stay like that no matter what happens to them. Some of them fluctuate because they have what you can call different isomers. They can have different stable structures and fluctuate between them. But generally speaking, they do acquire this relatively stable structure because the 1/r interaction is fairly strong between them in the right temperature range that they do form these molecules. So we have different groups of activity. We have ones that are basically axially symmetric, and they do translational propulsion only. So we met already AB and AB2. This is A2B3, and this is AB4. But these are stable in a different parameter range, so different valency that I described in that simulation. These are ones that spin, so they have spontaneous rotational propulsion. And this one is fairly easy to see, and also this one. These are inert because they are very symmetric, and essentially they don't have this kind of activity. And we also occasionally get exotic shapes like that. That's just one example. It forms spontaneously into this macromolecule, and often they do things as well, and so on. So it's an interesting game you can play, and here we only took these two classes. You can mix and match different types of activities and see what kind of structure you can make. So basically, you will have a recipe for making active colloidal molecules with given functionality. Now, I told you that I want to eventually study interaction between all these colloids, and if the colloids, so far my two colloids were isotropic, which means that they didn't really have any orientational interaction. If they do have orientational interaction, they will respond to each other's chemical concentration gradient in a number of ways. And to do that, basically, you can study an individual colloid in an externally created concentration gradient, first to see what kind of phenomenology you have there, and then you can take the next step and say, now I assume this concentration gradient has come from another colloid, and mix them together and see what happens. So basically, there are three different ways that an externally imposed concentration gradient will affect a self-diffusive phoretic active colloid. One is that it will modulate the strength of its propulsion. So it has this translational velocity, it has the spin. They depend on the local value of the fuel concentration. You modulate that, you modulate the strength of these activity, basically the strength of the activity in a local way. They are, however, so for example, if you look at the spontaneous translational velocity, that is, however, randomized because the orientation is randomized. So that means that you have something which is, it feels an effectively stronger fluctuation if you basically average over the orientation in some corners and less so in other corners. And this kind of phenomenon has been studied in the context of chemotaxis. You can look up a paper by Mark Schnitzer and some really nice work by Mike Cates and Julian Tailleur more recently. There are other ways that the gradient will affect the motion of the particle. There is a drift. So this is a term in the velocity which is proportional to the gradient with a mobility which could be both positive and negative. And that could have contributions from the reactant or the solute or the substrate which is being depleted and the product which is being introduced. So all of these molecules could have different signs. And by the way, the sign of the mobility mu coefficient basically is a statement about the differential of the Hamilton constant of that molecule with the surface with respect to the water environment. So you take a water molecule out, you put in, say, an oxygen. What's the difference between these two effective interactions? That could easily be positive or negative for different types of molecules. So that's the drift term. And then there's also alignment. So you have this particle. It has a different orientation with respect to the external gradient. It can turn because of the gradient. So this is the angular velocity, which will go like n cross grad s. S here is the solute concentration or the substrate concentration. And the coefficient could again have positive or negative values that, these are sort of multiple coefficients of expanding, say, mu around the surface in Legendre polynomials. And this is for the product. You will have to add that of the solute as well. So the only point of this is if you actually do the calculation, you can see that by changing these parameters, so let's say mu1 and mu2, the first and the second moment, you can change the sign of the response from chemotactic to anti-chemotactic way. And once it's rotating towards or against, it will add to the behavior, but in a complicated way because it's coupled to n. So putting all of these together, so remember we have self-propulsion, spin, drift, and alignment, which is all driven by and mediated by these chemicals. You can calculate basically you can probe the collective behavior of the colloids, and here is a sketch of the kind of behavior that we can get. As it turns out, so this has been derived by probing into the spectrum of the fluctuations of the density and the director field independently. So when density field becomes unstable, you will have something that you can call a cluster formation. When the orientation field becomes unstable, you can have something which you can call aster. And as it turns out, these two don't always happen at the same time. So you can have the possibility of aster condensation in a region where you don't have collapse instability in the parameter space, or you can have it where you can have them at the same time. You can also have spontaneous oscillations, and you can have screening, which was briefly discussed in a couple of previous talks. Okay, so, but I haven't told you what these two parameters are. These are basically humongous combinations of these mu's and alpha moments, and they have positive and negative signs, so they allow us to change these parameters. And for example, you can see here these lines. This is what happens when you experimentally tune the first component of mu. So you go from here to here, you cross two boundaries, sorry. Okay. So I just sketched the calculation for this most complicated case. And one thing I forgot to mention about the chemical story is that that story has an added nonlinearity coming from the Michaelis-Menten type behavior. So we are in two different regimes depending on whether we are on the linear part of the slope of dependence of the velocity on the concentration of the fuel, or we are in the saturation. And the behavior is very different in the two regimes. I can tell you a little bit about the details of the calculation in a simpler case, which is this case of thermotaxis, because basically response to gradient of temperature and irradiation by external light doesn't saturate like Michaelis-Menten rule. So I only have a linear theory in that aspect, and I can sketch it much more easily. And also I ignore the torque and spontaneous rotation, so spin in this case. So what do I have? I have these colloids that are somehow asymmetrically coated, let's say, with a metal. And then I have illumination. The metal cap absorbs light and generates heat locally. Because of the asymmetry, it generates a temperature gradient, and there's propulsion. But because of the local generation of heat, each of them will also act as a heat source for the other ones and generate a 1/r decaying temperature profile, which is felt by everybody else. So each one will have this arrow for propulsion, and then will sense the interaction coming from the other one of this long-range attraction or repulsion. And what determines whether the interaction is repulsive or attractive is the so-called Soret coefficient, which is the ratio between the off-diagonal Onsager coefficient to the diagonal Onsager coefficient, although it's not the right one, this one. So it could be both positive and negative. That was my point. The translational propulsion velocity of a self-thermophoretic colloid can be constructed similarly to what we had before. So here I have intensity of light times epsilon, which is the absorption efficiency of that metal coating on the cap. So this is my alpha. dt, which is thermodiffusion coefficient, is this off-diagonal Onsager coefficient, so it's velocity in response to temperature gradient, however it's made, and that can be both positive and negative, and I have to divide it by the relevant diagonal Onsager coefficient, which is the heat conductivity in this case. So if I do the maths, I get the 1/6 for the prefactor. So here it is. I have these guys generating the temperature and generating this velocity and having this self-repulsion. Simple equations. Again, Langevin dynamics. I can add the self-repulsion in this case, which I didn't have for my catalytically coated sort of colloids that made molecules. And then I have this gradient of temperature, which is evaluated at the position of the colloid. I add the noise, and this is my stochastic dynamics for the orientation. So eta here is the orientational noise, which will have a variance which is set by the rotational diffusion time coefficient. Temperature profile, you can assume that temperature relaxes instantaneously, and basically you have a bunch of 1/r centered at the location of each colloid. So each colloid acts as a heat source which is moving around, and then what it makes will affect the other ones with the 1/r potential.
So this is assuming that they're moving very slowly compared to the rate of thermal diffusion.
Yes, which if you put in numbers, so if you remember that tau d that I had, which was the relevant time scale for the dynamics of the medium, of the field, in the case of heat diffusion for a micron-size object will turn out around 10 to the minus 7. Around 10 to the minus 4 seconds. Whereas the rotational diffusion time will turn out to be around seconds, 3 seconds maybe, for a micron-size object. So there is a separation of time scale, and I
What about the time it takes the object to diffuse its own diameter?
That's the same as...
Try to translate its own diameter.
Well, diffuse its own diameter is the same as the rotational diffusion time, and translate is presumably even slower. I mean, faster.
The active transport.
Because the active transport adds to whatever diffusion you have, so I think it's a fair assumption. I mean, if you want to study shock waves and so on, you can, heat waves, but I think this is a fair approximation.
Sorry, and what about the heat source that you have in yellow at the top?
Yeah, that's a good question. So there are two aspects. One is I'm assuming uniform illumination from every side. I couldn't draw it, so I did this instead, which is very misleading, right? So it's not, I'm not considering the fact that this one can cast a shadow on, let's say, this one, etc., and the finite size. Also, so thanks for the question, I'm treating each particle as a heat monopole, which means that I'm, again, staying in the far field limit. So particles could get close to each other and could see that it's only this cap which is generating heat and not the rest of the colloid and so on. I'm ignoring all that in the lowest order approximation. And I can show that that is not going to matter for what I want to tell you. Okay, so you can take the Langevin equations and turn them into continuum equations for the probability distribution of finding a particle at position r and orientation t. This is a fairly straightforward formulation, but I appreciate that it might be painful to watch this for the mathematician colleagues in the audience because it involves Taylor expansion of delta functions and so on. But for what it's worth, it will give you something which works out if you're careful about details. You know, when you evaluate these coefficients in your Taylor expansion of a delta function. And the thing to notice in this equation is the nonlinear coupling between the gradient of the temperature field and the probability distribution. When you close the equation, you will have temperature generated by the probability distribution itself because this is the source of the molecules that are generating the heat. So you have basically this nonlinear coupling through the closure equation, which is Poisson's equation for heat conduction. I'm also assuming that diffusion coefficient for the translational diffusion coefficient for the colloid and rotational diffusion coefficient for the colloid are constant, which means that basically I'm doing linear response theory when it comes to regarding what happens when I change the temperature to the effective diffusion. And that is something which is, it's an approximation, I know a little bit about this field of Sore, and I know there's someone else in the room who knows more than I do, but I think it's fair to say that there isn't much more than this that we can do at this stage, and this is still an ongoing field. People are studying the effect of this particular aspect. But for me...
The divergence in the Fokker-Planck equation also includes derivatives with respect to n?
Yes.
Yeah.
No, not this one. So I have this rotational derivative, which gives me the...
So that's explicit there.
Yeah, so because I didn't put any dynamics in the orientation just comes off as a normal diffusion. Yeah, okay. So then there's a fairly straightforward way to basically take the hydrodynamic limit of these equations and describe the main slow variables for the density, for the polarization field, nematic order parameter, and so on. And then you get a hierarchy of equations which you need to somehow stop and you basically approximate and truncate and so on. We've seen this kind of thing earlier on in the audience and in the week, and many people in the audience are better experts than I am on this kind of calculation. But I do the simplest thing possible, which is basically stop at this level and here take the limit of long time and large length scale. And if you look at these terms individually, you can convince yourself that it's only this guy, 2d r times p, and the gradient of the concentration that will survive for a self-propelled particle. So assuming v naught is non-zero, and balancing these two will give you something for the polarization, average polarization field, which is minus the gradient of rho, which you can put back in the original equation and obtain an effective equation describing only the concentration profile. That is very similar to, say, the Nernst-Planck equation, if you have only one species of charge, and then you couple it to the corresponding Poisson equation. So these are the two equations we need to solve. You can solve them in stationary state. You get basically a Boltzmann weight for the density rho. Rho will be exponential of t, and you put it back in the Poisson equation. You get something that looks like Poisson-Boltzmann equation. So Laplacian of t is exponential of t, except that the sign here, which is set by Sore coefficient, could be both positive and negative depending on the sign of Sore coefficient. So I will skip, because my chair is up, what happens when there's repulsion, because that's a fairly straightforward thing to see. There is an interesting case when there is attraction, so Sore coefficient is negative. You get an instability. I'll just show this movie of concentration and temperature, and what happens is the instability basically predicts an instability in the temperature profile at some point, and that's basically a thermal explosion. And the explanation for that is the heat flux that's generated, say, at the boundary cannot be balanced in stationary state by the buildup of thermal energy inside. And if you look at the equation Laplacian of t equals exponential of t, that is in fact the equation that was first written in 1939 by Frank Kamenetsky to explain the onset of thermal explosion or in combustion reactions. It was the equation he had, and it basically, I took the solutions from those papers. And this phenomenon can be thought of, well, okay, I'll skip this. I guess I'll skip that as well. And just, well, I won't even go to that. So I'll just put up my conclusions. Thank you very much.
In that experiment where you have like chemical reactions going on, you know, at the surface of the colloid, do you ever get like gas bubbles or stuff like that?
Yes, that's a very good question. So gas bubbles will form when the rate at which you introduce one of the products is basically higher than the rate in which that product can dissolve, plus when that product can phase separate easily, given, you know, the conditions. And it turns out in this particular system, platinum and hydrogen peroxide, that depends on the size of the colloid, because basically that controls the effective number of oxygen molecules that have to be diffused around. And there is a threshold for the size, typically around 5 to 10 microns. You start seeing the bubbles if you use this platinum coating. And that changes the dynamics of the
But isn't that a difficulty for like you want to infer reaction dynamics from looking at how the colloids move? Because then like if they're like small bubbles that you can't somehow see directly, doesn't that kind of...
Okay, that's a very good point. So if for one thing, I have asked my experimental colleagues, and they tell me that they have looked with microscope and so on for these bubbles, because it's important to know when you want to isolate one particular mechanism for mobility, for motility, that you are excluding all the other options. And also, I think if you have really, really small bubbles that you cannot see every now and then, that will just contribute to the inaccuracy of the description. But overall, when you don't have the inertial effect of a bubble fizzing out, and changing the game because it's not going to be viscous anymore, or it will be a very different type of viscous motion, then I think you can approximate it reasonably well.
When you do experiments in a two-dimensional system, the concentration actually obeys the diffusion equation in 2 dimensions, whose propagator is the log, and doesn't that mean that their interaction...
You're talking about experiments or our simulations?
Studies. I mean, in your simulations, you are at liberty to use...
Yeah, so in real simulations, you usually have a substrate. And then you have a chamber, and then you need to decide what to do basically as boundary condition. And if you have 1 colloid or 5 or 10, it doesn't matter, because by the time you're doing the experiment, the number of excess molecules you're creating is not going to change things. There won't be a finite density of things. If you are looking at a finite density of colloids, then you have to devise a system in which you basically make sure that you sit at the neutral condition, which means if you are introducing effectively some molecules at a given rate because of the reaction, you have to remove it somehow. Sure. Either at the boundaries or some other way.
Yeah, but even then the interaction could be a log rather than 1 over r, right?
So the interaction will be a log when the thickness is smaller than the typical distance between them. That is true. But if you have a chamber which is, let's say, 20 microns, and you're looking at 3 micron distances, then I think it's...
I was just thinking, otherwise you get 2D Coulomb gas physics.
Yeah, that's an interesting suggestion.
Okay, so suggest that no certain questions we think Ramin again.